solve the nonlinear equations. So that method is called a secant method, and we will do its derivation and how this method is implemented. Then we do the comparison between the secant method and the Newton's method. So now the problems with the Newton method is that sometimes it is impossible to find out the derivative, or sometimes the derivative fails because of the Newton's method. So we cannot apply the Newton's method there. All the Newton methods is a very extremely powerful, fast converging method, but it has this weakness. So to avoid this derivative kind of function at each approximation, we move towards the secant method. What secant method do? It just requires the function values at that point, not the derivative at that point. We start with the derivation. So derivation is basically definition of the derivative. We have, for example, we are taking the derivative at point Pn minus 1, and function derivative at point Pn minus 1 is f dash of Pn minus 1 is equal to limit x approaches to Pn minus 1. Pn minus 1 is a particular point, and the function values, the difference of the function values divided by the difference of that values, x minus Pn minus 1. So that makes it f of limit x approaches to Pn minus 1, f of x minus f of Pn minus 1 divided by x minus Pn minus 1. So that is the definition of the derivative. Now we move further, and if Pn minus 2 is close to Pn minus 1, so in case of substitution, we just replace Pn minus 2 instead of x. So now the equation becomes f dash of Pn minus 1 is approximately equal to f of Pn minus 2 minus f of Pn minus 1 divided by Pn minus 2 minus Pn minus 1. So these are, suppose that these both are consecutive 2 points. One is the point Pn and its preceding point is Pn minus 1, and its preceding point is Pn minus 2. So these points are the consecutive points. So by replacing x by Pn minus 2 is for that purpose. Okay, so the derivative now becomes in the next step what we have done in the next step, that is using this approximation for f dash of Pn minus 1 in Newton's formula. Okay, what is the Newton's formula? Let me explain this thing. What is the Newton's formula? If I calculate the Newton's formula at point Pn and I use the previous points, then Newton formula becomes Pn equals to Pn minus 1 minus f of Pn minus 1 divided by f dash Pn minus 1. And if I want to write this equation in terms of derivative f dash Pn minus 1, then it becomes, I have to shift Pn minus 1 to the left, and it becomes Pn minus 1 equals to minus f of Pn minus 1 divided by f dash Pn minus 1. And what I do, I cross multiply it to get the derivative. So if I cross multiply this and I shift f dash of Pn from denominator to numerator, multiply this, it becomes f dash of Pn minus 1 equals to minus f of Pn minus 1 divided by Pn minus 1. Okay, so this is the first derivative, and in the equation A, I named it the equation A, and the equation A is f dash of Pn minus 1 is approximately equal to f of Pn minus 1 minus f of Pn minus 2 divided by Pn minus 1 minus Pn minus 2. We have extracted this equation A with the help of the derivative, and I just replace Pn minus 2 instead of x. So what we do, we replace this Newton's formula derivative equation in equation A. If I replace this, then the left hand side becomes minus f of Pn minus 1 divided by Pn minus 1 is approximately equal to f of Pn minus 1 minus f of Pn minus 2 divided by Pn minus 1 minus Pn minus 2. And if I cross multiply it, then this equation becomes minus f of Pn minus 1, and these two consecutive points, the Pn minus 1 minus Pn minus 2 is approximately equal to Pn minus 1 into f of, so these are basically two difference, product of the difference of two terms and two functions, consecutive functions. F of Pn minus 1 minus f of Pn minus 2. Now in the next point, what I will do, I will shift this f of Pn minus 1 minus f of Pn minus 2 to the denominator, and it becomes Pn minus 1 is approximately equal to f of Pn minus 1 into Pn minus 1 minus Pn minus 2 divided by f of Pn minus 1 minus f of Pn minus 2, and here Pn minus 1 is a negative number, so I shift it to the other side. Then this equation becomes Pn is approximately equal to Pn minus 1 minus f of Pn minus 1 divided by Pn minus 1 minus Pn minus 2 divided by f of Pn minus 1 minus f of Pn minus 2. So this is called, I name it as equation B, and this equation B is also known as, it's called the secant formula or secant method. It is also known as two-point method because we are using consecutive 2 points, next 2 points or previous 2 points. It's more accurate than if I say previous 2 points for the next root to be found. Okay, and also we can say it as, we can name it as two-point method or two-point approximation, and it is also known as straight line approximation. So there are basically 3 different names for the secant method or secant formula. Okay, so we have derived this formula that is called secant formula, and you know what is a secant line. A secant line in the circle, a secant line is the line that is basically it is a chord that cuts the circumference of the circle at two different points. It is basically a straight line, and the one secant line that cuts the circumference at 2 different points in a straight line, and it also passes through the center of the circle, is called the diameter of the circle, and the rest of the lines, straight lines, are called secant lines. Okay, so what is the procedure if we use the secant method to any non-linear equation? First point is that we must require 2 initial approximations. We can find it out with the Newton's method, but there is also the condition of the opposite signs is not required in this secant method. So the root or 2 initial approximation can be found by the Newton's method, but in most of the questions it is given. So 2 initial approximations are required, that is P0 and P1, to find out the P2. So the approximation P2 is the x-intercept of the line joining P0 f of P0 and P1 image of P1 is f of P1. So the and so on. So approximation in the next iteration, approximation P3 is the x-intercept of the line joining P1 f of P1 and P2 f of P2, and so on until the root repeats itself. Then we got the solution. Okay, note that only one function evaluation is needed per step for the secant method. Only one function. We don't require the derivative. Okay, only function value at the 2 consecutive values at the 2 consecutive points, and just apply it in the formula. In contrast, each step of the Newton's method requires an evaluation of both the function and its derivative. So derivative point is negligible here. Okay, here is the example, and the example is it is a transcendental function and polynomial function. Also x is polynomial cos of x, so combination is transcendental function. So f of x is equal to cos of x minus x, and its initial approximation is given, and it is found out by the Newton's method. And first one is P0 is 0.5, okay, and P1 is pi by 4. So pi by 4 is 180 by 4. so that is 45 degrees. Further, we start with these two initial approximations to find out the P2. So if I apply this formula, P2 is equal to P1 minus f of P1, and basically f of P1 is f of 45, Pn minus 1. So P1 minus P0, that is 5 by 4 minus 0.5, 1 by 2, divided by f of P5 by 4, that is the value. You can write it f of f of 5 by 4 minus f of P0. F of P0 is 0.5. So you can sort out the function values, and the first one is the function value, that is f of P0 is minus 0.078, and you can use this up to tolerance of 4 decimal places. In this, it is given, this example is given in 1, 2, 3, 4, 5, 6, 7, 8 decimal places. So almost 4 decimal places are enough for it. I use this for secant method table. Okay, so and for finding out the P2, first point is 0.5 and second point is 0.7364, and in the next iteration, if I want to find out P4, then first iteration is for P2. I have determined the P2 with the help of P0 and P1, and that is 0.7364, and in the third iteration or second iteration, P3 is determined, and that is by using that secant method formula. It is 0.73906. Okay, for finding out the P4, P4 is extracted from P3 and P2, and P4 is 0.7391. Okay, so now I can see the rule starts to repeat it. So for finding out the P5, P4 and P3 is required, and by using the secant method formula, function at that point, and if your one point has the function value up to the tolerance 0.0000, so that means your root starts to appear and it gets repeated again and again. And for while finding out the P5, we have P5 is 0.7391. So 0.7391 starts from the P3, that is second iteration. So now your roots appear, and that is 0.7391. Okay. In the Newton's, if I apply the Newton's method, then it is also, the root is also here. Root is also here 0.7391, but Newton's method is far more fast conversion method. But secant method here also shows that correct up to. And one more thing I find out, yes, Newton method is more accurate than secant method, fast conversion method, but secant method is also a very good method because it doesn't require the derivative, and we don't have any problems with the derivatives, impossibility of varying derivatives here. And also, what else? It is accurate up to 10 decimal places, and whereas Newton's method accuracy is up to, yes, it is. Yes, we compare this basically one question with the Newton's method, and the other method is with the secant method. Okay. So comparing results, we can see that secant method approximation P5 is accurate to the 10th decimal place, whereas Newton's method obtained this accuracy is P3. So that means Newton's is more fast conversion method, and here the conversions of the secant method is much faster than the functional iteration, but slightly slower than the Newton's method. But this method is far better than the bisection method. If I use the bisection method here, it will reach up to the 15 plus iterations. So this is all about the Newton's and secant method. method. Okay, I hope that you understand this method, and if you have any questions you can ask me.